So today we're going to talk about basic principles of chemical analysis. And I mean really basic. What is chemical analysis? How do you choose to analyze something? And why? And how can you be careful in your analysis? So when I talk about what an analytical chemist does, I usually do this in one of two ways. The first way is the way I usually explain things to non-scientific friends, where I talk about how if there's a recipe that you really want, let's say it's from a restaurant you go to, but it's really expensive to eat your favorite dish there, you wish you could duplicate it at home, and so you're trying to figure out what the recipe is. And this is something that chemists can do. We may not be looking for food recipes, but we can figure out what something is made of and how much of that thing there is inside the thing that we're analyzing. So that's the first thing that we can do. Sometimes when we are looking for a recipe for something, we're looking for a recipe for one particular thing. Like, here is this compound that we got out of something herbal that we know people have traditionally used for a cure for something. Maybe we can figure out what makes that chemical work. And to do that, we have to know what the chemical is composed of. What's its molecular formula. Sometimes we're looking at a system, like the ocean, right? What are all the many things that make up the ocean? And it's not just what's in there, it's how much. Everyone knows with a recipe, you can have a recipe that tastes really good with 1 teaspoon of salt, but if you put in a cup of salt, suddenly the recipe tastes differently. Everything behaves differently, depending on how much there is of everything. So that's sort of the non-scientific approach to explaining analytical chemistry. Now let's talk about a few other things that analytical chemists do, which basically revolve around method development. How do I measure what I want to measure? There are some things that we want to measure that we don't know how to measure yet. And so coming up with those ways of measuring things is a real challenge. Sometimes we do have ways to measure things, but they're really not very good ways to measure things. So how can we make a better way to measure what we want to measure? And part of that method enhancement process is the two questions that are next. How much do I trust my measurements? Which could be a class, year-long class in and of itself. And also, am I really measuring what I think I'm measuring? And so those are the sorts of things that we're going to touch on today so you can understand what we look at when we are trying to analyze something very specific. So when you are doing a chemical measurement, in very vague terms, here is what you are doing. The first thing is you're looking for something that you call a differentiating characteristic. In other words, for the particular analyte that you're trying to measure, what is something that makes it react differently than everything else in your mixture of stuff? If you can pick out one of those differentiating characteristics, then you create a probe, something that will interact with that differentiating characteristic. I know this is very vague. We'll give a real-life application later. So next you're going to anticipate the response to the probe. If you do whatever this action is that interacts with your differentiating characteristic, what will the output be? So there are many ways that you could find outputs, right? You could have, I do this thing and then my analyte produces light. I do this thing and then my analyte changes color. I do this thing and my analyte generates electricity. Okay, so all of those things are sample responses to your probe. Well, the next part is to actually measure that response, and this is why you have to anticipate it, because obviously if you're going to measure something, you need to know what to measure, right? If something gets larger in response to your probe, then you're going to need to measure the size. If something produces electricity, you're going to have to measure how much is generated. If something puts out light, you'll need to measure how much light is being produced, right? So that's why we think about these as two separate steps. Next, you get to interpret the measurement data. So you're going to get some sort of output, and the output is almost never the output that you want. So how do you turn the output of your instrument into some sort of information that your brain understands and can make sense of? And then finally, you're going to assess the limitations of the technique. In what way could your measurement be off? And that kind of goes back to, am I really measuring what I think I'm measuring, and how much do I trust these measurements? So let's go through a real life example. So here is a dinosaur of a scientific instrument. It is our campus atomic absorption spectrometer. And let's think about how this operates. When we are looking for elemental analysis, especially when we're talking about metals, if you do something to put those metal atoms into an excited state, they will generate light. And they will generate that light not as a continuous spectrum like we see out of a white light bulb, but with very specific wavelengths of light. So the ones I talk about in my Gen Chem lectures are sodium and hydrogen. We love talking about sodium because, of course, there are street lights that are sodium vapor street lights, and those have that very distinct orange tinge to them. But it's not just these two elements. Many metals emit light at different wavelengths. And so for these metals, that can be a differentiating characteristic. The AA is designed to take advantage of that differentiating characteristic. If we want to use that differentiating characteristic of emitting in specific wavelengths as a tool for identifying metal cations, then what we need to do is we need to come up with a probe for looking at that differentiating characteristic. Now remember, this characteristic only occurs when you excite something to higher energy levels, and so we need something that's going to excite it to higher energy levels. And that's going to be our probe. When you put a solution of potassium into the AA, you will see that it burns purple because potassium does emit that nice violet light. But it's not enough to look at that purple and say, oh, look, there's potassium in here. We usually want to know how much potassium there is. So we could say, my probe is, I'm going to excite this to a higher energy level, and in this particular case, we do it by throwing the sample into a high intensity flame. So the response is going to be light emitted at a certain wavelength. And now we're going to measure that response. How do we measure that response? In the case of this AA, what it does is it takes a photomultiplier tube that counts photons, and we also have a monochromator that picks a specific wavelength, so you're only looking at light photons of one particular wavelength, and it turns that photon input into electricity. So how do we measure the response? In this particular case, we measure it with voltage. Now remember, the next step is to interpret the measurement data. So if you run stuff on the AA, what you're getting out is you're getting a reading in millivolts. But if someone asked you how much potassium is in your seawater sample, You don't say, I have 339 millivolts worth. This is why we need to interpret our data. Sure, we get raw measurements, but those measurements don't mean anything to a chemist who really wants to know things in terms of concentration, not instrument output. And so what we need to do is find a way to turn this into a measurement that we understand of concentration. So on the AA, we do that by having a calibration curve of things that have known concentrations, and we look at the output in millivolts for things of known concentration, and we use that to calculate the concentration of our samples. The last step is, of course, to assess limitations, and that is a little harder when it comes to AA. So let's go back and let's look at a different method. First, let's review what analytical chemists do, and let's look at method optimization. Here are the two questions that we really want to talk about. How much do I trust my measurements? Some of that is my instrument flaky or is it reliable? We definitely get a lot of that at a school where we have older instruments. But even if you have a perfectly functioning instrument, there are limits to what your instrument can do. So we need to talk about that. And also there's the question of, am I really measuring what I think I'm measuring? So what I'm going to do here is I'm going to go to a very low-tech solution. I know you thought the AA was low-tech. Here's an even lower tech, an older way of evaluating things. And that is the colorimetric determination of silica. So this is something that I love to do in my analytical chemistry labs because it teaches really important principles of, am I really measuring what I think I'm measuring? So first, let's go back and let's look at some of these questions. What's the differentiating characteristic here? This is a colorimetric method, so the differentiating characteristic is the thing I want to analyze turns a different color. In this case, the silica in the water combines with our colorimetric agent and it turns a blue color. Now, how would we measure the response to this probe? Right, the probe here is the colorimetric agent. The response is it turns blue. How do we measure that? We measure that with a UV vis spectrometer. And we use that to get absorbance data, right? So that's our raw measurement. How do we interpret that measurement data? Well, we again have a calibration curve like the one that we see here where we have different concentrations. The dark one is the most concentrated, the light one is the least concentrated, and we can use this to turn the absorbances for our unknown sample into a concentration that we trust. What limitations does this technique have? When I ask students to write up this lab report, a lot of times what they say for limitations is, I'm not very good at pipetting, so my concentrations could be off. Sometimes they'll say, I don't really think this is a very good UV vis spectrophotometer, things like that. But this technique has even more fundamental issues with it. And to understand those, what we need to do is we need to go to the standard method from which this particular lab is derived. And it has this whole section called interferences. And there are two sentences in this section that I want to zero in on. First, phosphate produces a similar molybdate complex under certain pH conditions. Phosphate reacts to our probe the same way that silica does. That's a problem. So you could get a measurement and you could think that's your silica measurement, but that could actually be some silica reacting with your colorimetric agent and some phosphate reacting with your colorimetric agent. And so what you think you're measuring, silica, may not be what you're actually measuring, silica and phosphate. Okay, there's another set of interferences here. Hydrogen sulfide and ferric and ferrous iron apparently interfere with the determination. Now here it's not clear how these substances interfere with the method. It's possible that, for example, iron could bond with phosphate that keeps phosphate from interacting with a colorimetric reagent, or iron could also interact with a colorimetric reagent, and we don't know, they don't specifically say how this interferes. So what you need to understand when you hear people talking about interferences is they're telling you this is a limitation. These are things that could cause you to get a different reading than what you think you're actually measuring. Now, conveniently, a lot of these interferences have fixes. So for example, when we do this lab, students get to pipette tartaric acid into the beaker along with a sample. And we generally do this as part of the standard method because in natural water systems where we're commonly measuring silica, there's often also some phosphate. So we just assume the phosphate is going to be there, and we've done something to eliminate the phosphate interference. We can deal with the iron interferences by adding disodium EDTA. And in fact, we do this every time we do this lab. You'll notice that it says hydrogen sulfide may be removed by boiling an acidified sample, and we do not do that every time. And the reason we don't do that every time is because hydrogen sulfide stinks, and usually if you have hydrogen sulfide in your sample, you can smell it. And if you smell it, then you boil your sample. If you don't smell it, you assume that hydrogen sulfide is not there, and you don't boil it. Now, is it possible that hydrogen sulfide might be present in such small amounts that you just can't smell it? Or is it possible that your nose is really stuffed up because it's allergy season and you don't smell it? Yes, that's a limitation of this method, is that if there's hydrogen sulfide and you don't do something with it, then it may affect your final concentration and you may not even know it. So you always have to think about limitations like this. So if you devise a probe and more than one thing reacts to that probe, and both of those things that react similar to the probe, so you can't differentiate the response from those two things, what are you going to do? There are three possibilities. The first thing is use a different probe. Come up with a different colorimetric agent. We have not come up with a good one for silica, and that's why we add all these different things to get rid of interferences. But if you're measuring phosphate, you could use this same thing, assuming that you're measuring something that you don't think has silica in it. But there are a whole bunch of other colorimetric agents that will bind with phosphorus and don't bind with anything else. The next thing you could do is find a way to separate those two analytes before you analyze them. If you had magic molecular tweezers that could go through and pick out all the different phosphate molecules before you ran your silica analysis, wouldn't you use them? Well, of course, there aren't magic molecular tweezers, but there is such thing as separation technology. There are many different kinds. Many of these are what we call chromatography, gas chromatography, liquid chromatography, high pressure liquid chromatography, electrophoresis. There are a whole bunch of different things that you can do to separate stuff. Sometimes what you need is a more sensitive detector. And so what I'm going to do here is I'm going to talk about this in regards to yet another instrumental technique, and this is mass spectrometry. Specifically, when I was doing isotope analysis back in grad school, one of the things that we did was we used oxygen 18 to track a process. So the oxygen 18 was the probe for a process, and we had to measure that probe. We measured it with a mass spectrometer. Most oxygen, remember, is oxygen 16. So if you have O2 made of oxygen 16, you have something with a mass of 32. If you have O2 made with oxygen 18, and this process produced oxygen that was only made with oxygen 18, then you would end up with a mass of 36. So that's how we could measure. Now, there was a problem, which is that molecules that are made up of two oxygen 18s are not the only thing that has a mass of 36. Specifically, our atmosphere contains argon. Most of it is argon 40, but there's a reasonable amount of it that is argon 36. How do you deal with this? As it turns out, the GC mass spec that we were using had a quadrupole mass spectrometer, and that could not distinguish between these two. We had the mass 36 oxygen 18, the mass 36 argon, and those would come out at exactly the same time, and they would hit the detector, and the detector would not be able to tell them apart. So what we had to do was we had to implement a process so that the oxygen and the argon would pass through the gas chromatograph at different speeds. And we had to cool everything down with liquid argon, and it was super cool, if you'll pardon the pun. And that's how we did it. So we saw two peaks that had a mass of 36, but they came out at different times. We could measure them separately. So that was the second technique that I talked to you about. But what if we didn't have that instrument? What if we had something that was more sensitive? When I talk about more sensitive, the way that chemistry students tend to understand this is with balances, right? You have some balances in your chemistry lab where it goes to like 0.1 gram, and then you have the analytical balances which go to 0.1 milligram. Right, so you can measure a lot more precisely on those analytical balances than you can on the less sensitive top-loading balances. So as it turns out, you can get mass spectrometers that are far more sensitive, and you can't really do it with a quadrupole mass spec, but if you have the sorts of mass specs that you use for isotope analysis, so even though this oxygen molecule has a mass of 36, that's 2 sig figs. What if we knew that to more than 2 sig figs? And the mass could be written as 35.998. The mass of an argon 36 is 35.967. So if only you had something that could measure to 2 decimal places, you would be able to tell the difference between these two molecules. And so when we say get more precise measurements, that's what we're talking about, is to measure things with more precision so we can get more significant figures, and that helps us to distinguish between the two analytes. So really, this is what it comes down to. You're looking for ways that your analyte behaves differently than all other analytes in your mixture, and you're finding a way to measure the way that it behaves differently. That's chemical analysis in a nutshell. Hope you enjoyed this video, and I will talk to you soon.